if you wanted to identify an unknown molecule, you can't take the just NMR and predict what is going to be the structure. What you really do is you get some information from nuclear magnetic resonance, proton NMR, C13 NMR. You get some information from ultraviolet spectroscopy. You get few information from infrared spectroscopy. You need to collect the molecular mass information. For that we use mass spectra. So each spectra contribute to the structure of the molecule in terms of certain informations, and we need to compile all those information and get into the conclusion that the structure of molecule is so and so. Then let us see what is the actual idea behind infrared spectroscopy, where this infrared radiation will influence in terms of the energy of the molecule. Let us see. So infrared spectroscopy is also called vibrational spectroscopy. So just before I was asking where the infrared radiation influence in terms of the energy of the molecule, that is the vibrational energy. So the vibration is influenced by the infrared spectroscopy. The infrared spectroscopy is widely used in both the research and industry as a simple and reliable technique for measurements, quality control and dynamic measurement. These are the broader applications of infrared spectroscopy. What does this technique measure? Let's see what does this technique measure. IR spectroscopy measures the absorption of IR radiation by materials, and the atoms vibrate about their bonds. So, if there is a vibration about their bonds, IR radiation will be absorbed, and this absorption of IR radiation is measured by infrared spectroscopy. And the IR spectroscopy is primarily used to identify the bond types, structures, what type of bond is it, single bond, double bond or triple bond, or it is having any heteroatom, structures, what type of structures it is having, what are the functional group present in the organic and inorganic compounds. Why IR absorption spectra is important? Absorption spectra is important because it enlightens about the structure of the molecule by absorbing IR radiation because the molecules absorb IR radiation at frequencies related to their unique composition, structure, and the numbers, types and strength and position of the bonds. So the absorption depends on all these factors. So it gives a lot of idea about the structure of the molecule. So let us have an idea about the electromagnetic radiation. This is what you are seeing is the electromagnetic radiation. As you move from this side to this side, you could see that the energy is increasing and the wavelength will be decreasing in the opposite direction. So infrared refers to that part of this electromagnetic spectrum between the visible and microwave region. This is that region. How potential energy is stored in a molecule. Now we were talking about the light, which is going to be the molecule will be exposed to light, so we need to know what is light. And what about how the light get a scope to interact with the molecule? So how light is getting a scope to interact with the molecule, if you ask? You need to know how the potential energy is stored in a molecule. The energy of a molecule consists partly translational energy of a molecule. Suppose if you take a mug of water, a glass of water, if it is too hot, that means the molecular motion, water molecules are running from one place to another place in order to withstand this hotness. So that is translation motion. And partly rotational energy, the molecule will be keep on rotating. Partly vibrational energy, the atoms will be vibrating within the molecule with respect to the equilibrium position. And partly electronic energy, and the electrons are shared in between. They have the capacity to absorb energy. They absorb energy in order to get transit from lower energy to higher energy. All this vibration, everything will be happening. If they absorb energy, it will be going to a higher energy level. So we can say that the molecule store their energy by executing some sort of motions, maybe, or by means one part of the molecule, that is the electron, they acquire energy and get excited. They will acquire more energy. So once they execute these type of motion, they need energy. That energy could be absorbed from outside and it will be encashed in terms of translation, vibration, rotation. Plus within the molecule only one, means not one, actually a part of the molecule will absorb that energy. That part is nothing but electrons. Electronic energy transition normally gives rise to absorption of emission in the UV and visible region of the electromagnetic radiation. So actually, if you take the electronic level, we'll be discussing about that. The energy is quantized. So if you talk about the energy level, one level is having lesser energy than the other level. So if you wanted to take an electron from lower level to higher level, you need a particular amount of energy. So the interesting fact about the molecules or atoms or electrons, their energy is quantized. They won't take whatever be the energy they get. They won't satisfy with the lesser one. They won't be so happy by absorbing the more energy. They need a particular energy because that defines the internal structure of the atom or molecule. So if you are expecting electronic transition, the energy what you need to supply is the visible or the ultraviolet radiation. Pure rotation gives rise to absorption in the microwave region or the far infrared region. So the molecules are getting rotated. You know rotation. And this rotation, it does not require much amount of energy. It need energy only in microwave region. It is lesser than infrared. Okay. After micro only radio wave comes. So the radio wave is having least amount of energy and more wavelength. That's why it is utilized for the broadcasting purpose. So just adjacent to that microwave comes. So it need lesser energy, rotation, motion. Molecular vibrations. And the molecular, we were talking about the visible light will be utilized for electronic transition. And the next to next microwave, that will be utilized for rotational motion. So you can call the rotational spectroscopy or microwave spectroscopy. And in between what comes the infrared radiation. If a molecule is absorbing infrared radiation, there is something to do with the vibration of the molecule. That's what you have to understand. So molecular vibrations give rise to absorption band throughout most of the IR region of the spectrum. This is what the basic thing about the means what type of radiation will be utilized for what type of motion within the molecule. And if you talk about the infrared, this is the infrared spectrum. So you could see that this is visible and microwave, in between the infrared comes. And you have already learned about the theoretical part of the vibrational radiation. And if you recall, the near infrared can excite overtones and harmonic vibrations of molecules. And the mid-infrared may be used to study the fundamental vibrations and the associated rotational vibrational structure. And the far infrared may be used for rotational spectroscopy. We have already discussed. And what about the radiation? We have already told about the region, all those things. And what are the characteristics of a radiation? Wavelength and frequency are inversely related. We know that nu is equal to c by lambda and lambda is equal to c by nu, where c is one of the most accurately determined. The constant is what we call velocity of light, 3 into 10 raised to 10 centimeter per second. The energy is related to wavelength by frequency, that is equal to Max Planck's quantum theory. Energy is absorbed or emitted in the form of small packets of energy, and each packet is called quanta. Each quanta is having an energy related to E is equal to h nu. That's what this equation. It could be rewritten as hc by lambda when you take the previous equation into consideration, where the h is called Planck's constant, 6.6 into 10 raised to minus 34 joules per second. And note that the energy is directly proportional to frequency and inversely proportional to wavelength. And there is one more factor directly proportional to, that is wave number. So the energy is directly proportional to frequency and wave number and inversely proportional to wavelength. The reciprocal of the wavelength is called wave number. So it is directly proportional to the frequency and energy. IR radiation does not have enough energy to induce electronic transition as seen with UV. So you recall the electromagnetic radiation diagram. There you could see the ultraviolet is having more energy than infrared. So infrared is not fit for the work done by the ultraviolet radiation. Infrared spectroscopy works because the chemical bonds have specific frequencies at which they vibrate corresponding to the energy levels. So please understand, like there is a vibration. There is a vibration here. Now what happens if I supply the energy? The vibration will become more vigorous depending on the energy is absorbed. So in order to vibrate, this was the vibration range before, it needs some amount of energy. And after some time what will happen? It will get excited, vibrationally excited. So here it requires more energy, but that energy also quantized. Infrared spectroscopy works because the chemical bonds have specific frequencies at which they vibrate corresponding to energy levels. Infrared radiation is absorbed by molecules and converted into energy of molecular vibration, is what we would say discussing. When the radiant energy matches the energy of the specific molecular vibration, absorption occurs. So I said that this is E1 and this is E2. So if you take this is E1 and this is E2. Okay. So if the infrared radiation means it's a wide spectrum. One of the radiation is very suitable for this gap. Then what happens? That radiation will be absorbed and the molecule will get vibrationally excited. That's what you have seen. Absorption occurs, weaker the bond requires lesser energy. So we are getting into the infrared spectroscopy part, and one of the moral from the topic is, or one of the take home fact, that is, weaker the bond requires energy that is lesser, as if the bonds are springs of different strength. So if there is a spring which is really strong, then you need to supply high energy. If there is a spring it is having very weak, then what happens? It requires lesser energy for vibration. If the spring is strong, it requires more energy. So the spring means it is the chemical bond. Please keep in mind. So let's recall what are the type of vibrations it could be possible in a molecule. The stretching is possible, change in interatomic distance along with the bond axis. Stretching means it is change in interatomic distances. There is stretching vibrations. It could be symmetric or asymmetric, in plane rocking, in plane scissoring, out of plane wagging, out of plane twisting. You have already learned about all this in the theoretical part in the previous semester. Bending means there is a change in angle between two bonds. There are four types of bonds. There are four types of bends: rocking, scissoring, wagging, and twisting. Then, for a vibrational motion to be IR active, the dipole moment of the molecule must change. So, you have learned about dipole moment. What is dipole moment? We just discussed. Please understand, we have discussed one point: weaker the bond, lesser the energy. The same way, there is one more point from this. That is, for a vibrational motion to be IR active, if you wanted to observe IR spectra for a molecule, the dipole moment of the molecule must change by absorbing the radiation. If there is a scope for changing the dipole moment by absorbing radiation, then it is IR active. And there is a very equivalent one, like a complementary one spectra. That is what we call Raman spectroscopy. In Raman spectroscopy, Raman activity is there. Raman activity is associated with changes in electronic polarizability. We have discussed about polarizability. Polarizability is a property of bond associated with particular atom, electronegativity difference, all those things. So, for IR, dipole moment change. For Raman, electronic polarizability. That's the criteria. What is dipole moment? Dipole moment is actually, it is equal to, dipole moment is equal to the product of the charge and the distance between the atoms or the oppositely charged centers. See here, there are A is an atom of a molecule, B is another atom of a molecule, and this is the distance. So this is having a charge and this is having a charge. So mu is equal to delta into D. Delta is nothing but the charge, D is the distance. And please understand, a dipole moment is a vector quantity. It has both size and direction. Where mu is the bond dipole moment in coulomb meter, delta is the amount of charge at either end of the dipole given in coulombs, and D is the distance between the charge in meters. Now, quantization. Energy is said to be quantized when it can only be in certain discrete amount of levels, or it is quantized in packets of energy. That's what. Like many other type of molecular energy, bond vibration energy is also quantized. Just like electronic energy, vibrational energy is also quantized. That's what we were discussing about. I have drawn some vibrational picture. The frequency and the vibration is limited to discrete levels. Excitation from lower vibrational quantum level, ground state, to higher energy level, excited state can occur only by absorption of the photon whose energy exactly matches the energy difference between the energy levels. The energy difference between the energy levels is not same for all the molecule, but instead varies with the molecular structure. This is the point. Bonds are different, atoms are different. So what happens, like the vibration also will be different. When the vibration is different, the absorption of infrared also varies. There only we are having a scope for understanding the molecular structure and using this infrared as a tool to understand molecular structure. If we can figure out the relationship between the structure and the delta E, that's what the task. We might be able to use delta E to deduce the information about the structure of the substance. So there is a gap. Why this energy gap? This energy gap is due to the internal structure, and the energy is this much, And why this much amount of energy? That the answer will be the structure of the molecule. So if you can connect both, you can understand, you can use an infrared spectroscopy as a tool to understand. And to some extent, the relationship can be approximated by the amount of energy absorbed, and the internal structure could be little understood, to some extent understood by Hooke's law. Please understand, we are taking spring, a spring. The spring is in place of bond. The frequency of the vibration of the spring is related to the mass and the force constant of the spring. That is called K by the following formula. So this equation where K is the force constant and M is the mass and V is the frequency of the vibration. Please understand. And according to Hooke's law, two atoms and the connecting bonds are treated as a simple harmonic oscillator composed of two masses. The masses means nothing but atoms joined by a spring. So the behavior of the spring or the bonds can be described by the following equation. That is, nu is equal to 1 by 2 pi c into F by U, where this U is the unified mass m1 into m2 divided by m1 plus m2. C is the velocity of the light and he is the force constant, the stiffness of the spring. Ma and Mb are the masses at the ends of the spring. The second expression is called reduced mass or unified mass. According to the equation, F is proportional to the bond order, force constant, bond order and the mass of the atoms. Also, stretching frequency is related to the energy by Planck's equation. So according to the equation, F is proportional to, what is F? Here this F is proportional to the strength, like bond order. If single bond is there, weak. Double bond is there, bit strong. Triple bond is there, more strong. And this could be associated with the energy of the light. For example, if you take, this is allyl chloride. In allyl chloride, there is a CC bond. Here also there is a CC bond. This is single bond and this is double bond. And you know already, like the bond order increases, the strength of the bond increases. So, and its strength, the double bond harder to stretch than the single bond. So, it is easy to stretch single bond, so it vibrate more. So single bond occur at lower energy and the double bond at higher frequency. So you got the idea. Single bond is weaker, so lower energy. Double bond is stronger, so higher energy. So the take-home message it is, when comparing the bonds between same two atoms, bond stretching frequency increases with increasing bond order, as you have seen in the example. Now in this, there are two type of bond, that is, one is CH and CCl. Because Cl is a big atom, hydrogen is a small atom. CH and Cl bonds differ in the mass of the atom attached to the carbon according to Hooke's law. As the mass of one of the atom increases, the reduced mass decreases. We have given an equation for reduced mass. Smaller the reduced mass, decreases the stretching frequency. So, an sp3ch bond occurs at sp3ch bond occurs at 300 to 2800 per centimeter, and sp3 CCl occurs at 830 to 600. This is sp3ch. Okay. So sp3ch is having a smaller atom, so the reduced mass is more, so stretching frequency is more, whereas for this reduced mass is less because of the more weightage of more reduced, the higher the mass of chlorine, smaller the reduced mass, and when the reduced mass is smaller, the stretching frequency also increases. Understanding the take-home message is bond stretching frequency increases with increase in the size of the bonded atom. Bond stretching frequency increases. So listen, there is a CH. The CH and CCl bonds differ in the mass of the atom attached to carbon according to Hooke's law. As the mass of one of the atom increases, the reduced mass increases. As the reduced mass increases, the stretching frequency decreases. Greater the reduced mass decreases the stretching frequency. Please understand. And here it is not sp3ch occurs at 300 to 800, 3000 to 2800 cent per centimeter, whereas in sp3ccl occurs at 830 to 600. And there is a small correction I made. Bond stretching frequency decreases with increase in the size of the bonded atom. So if the atomic size increases, reduced mass increases. As the reduced mass increases, stretching frequency decreases. Bond stretching frequency decreases with the increase in the size of the bonded atom. So as the atom of to a carbon particular as the atom attached to a carbon, a particular atom, say a carbon, increases in mass, the reduced mass increases and hence the frequency of the vibration increases. So please look at this example. So let us take CH, CC, CO, CCl, CBr and Ci. So I have written in the increasing order of mass. So CH it is as we have discussed it on infra 3000. This is 1200 per centimeter. Then this is 1100 per centimeter. And this is 750. This is 600. And this comes around 500. So you could see that the decreasing stretching frequency because the mass attached to the carbon, mass of the atom attached to the carbon increases. So the moral of the story, the stretching frequency is related to the functional group. Functional group means it is an atom or group of atom which determine the chemical property of the molecule. So in real life what happens is if there are more atoms, there will be more bonds. Then the more complex the molecules may have many bonds, and vibration can be conjugated, leading to infrared absorption at characteristic frequencies that may be related to the chemical groups. This will produce a more complicated spectrum. So when unknown compounds are analyzed, a full spectrum is normally run. The goal is to identify the presence of a particular functional group and determine its location on a non-molecule. So the prediction is made. What prediction is made by IR spectra? If you ask, it is the presence of a particular functional group and determine its location on a non-molecule. So in the next class, let us discuss about how the various stretching frequencies are related to various types of